Hello everyone, this is Group 5 and our group project is air sparking recommendations. Firstly, let me introduce you what is airstripping. Airstripping is the process of moving air through contaminated groundwater or surface water in an above ground treatment system. Airstripping removes chemicals called volatile organic compounds, or we can also call it VOCs. VOCs are chemicals that easily evaporated, which means they can change from a liquid to a vapors. So basically, airstripping is trying to transferring of VOCs components from a liquid into an air stream. And this is an environmental engineering technology used for purifications of groundwater and wastewater containing VOCs. As I just said, since the VOCs, it's really easy to vaporize out of groundwater and get into the air. So the main goal for the air stripping is we were trying to make sure the concentration of the VOCs are getting as low as possible when admitted to the air. Most of the air stripping system were taking place in a packed tower or aeration tank. And also, through any devices that promotes contact between air and water stripping, some volatile compounds, air strippers are usually packed powers.
There are three main types of strippers used in remediation practice. They are packed column air stripper, low profile sieve tray air stripper, and diffused aeration air stripper. For the packed column, it consists of a cylindrical column that utilizes level of packing material and a countercurrents of airflow to remove VOCs from the wastewater. The low profile sieve tray system is similar to the packed column, with its main differences being horizontal flow of wastewater and the use of perforated trays through which air bubbles are passed to strip VOCs. Last but not least is the diffused aeration stripper. The wastewater enters into a large vessel with air diffusers installed at the bottom. As air bubbles float up, so do the VOCs, leaving a clean effluent as the final product. Here are some illustrations of a packed column stripper to help you better visualize how the system works. Some key equipment needed for this operation include a pump to transport wastewater, a blower to, of course, drive airflow upwards, and some screens and covers to capture the removed VOCs. Also make sure to note the height and vertical flow of water in this system. If a company wishes to install a packed column, they have to ensure that enough room and space exist to do so. Like I've said before, the sieve tray system operates similar to the packed column stripper. But in this design, the wastewater flows horizontally across the perforated holes, resulting in a shorter structure since the effects of gravity aren't as crucial. And like the packed column, a series of pumps, blowers, and screens are needed in order to maximize the efficiency of this system. The diffused aeration stripper offers the most simplistic design when compared to the other two systems. It only requires a tank to hold the wastewater and diffusers lined at the bottom that release air bubbles to strip the VOCs away. Other equipment that may be needed include a compressor and a pump. But with these units, a longer residence time means a better removal efficiency. And in order to achieve this outcome, companies would need a large area of space and a slower flow rate to allow the wastewater to be treated accordingly. In remediation practice, the two most popular systems are the packed column and sieve tray strippers because of their ability to remove over 99% of VOCs. Some benefits of the packed column include a wide range of airflow rates and is more cost-effective than the sieve tray system, as it can reduce the cost of treating air emissions. But the packed column can be victim to fouling if wastewater contains concentrations of iron, calcium, manganese, or biological growth. Also, the tall height of the unit might be a potential issue for companies with limited space. If fouling is expected to occur, then sieve tray strippers will be desirable as the trays can be easily disassembled for physical removing of the fouling. Also, this system is smaller and more compact, which can be a huge help for companies with limited space, giving it an edge over the packed column stripper. But with this accessibility comes a few drawbacks. The sieve tray system is generally more expensive and has a narrow range of airflow rates. Moving on to the diffused aeration stripper, which is the least popular choice in remediation practice. This is due to the fact that it is usually at a lower VOC removal efficiency and requires a large area in order to produce optimal results. But the pros of this system include its simplistic and cost-effective design, its ability to handle suspended solids, and offers resistance to fouling. This table lists typical VOCs that are often found in contaminated waters, and possible streams they can infect include groundwater, source water, and wastewater, along with sources of contamination that range from gasoline and solvents leaks to disinfection byproducts, pesticides, and plastics and refinery waste. This design flow path for air stripping starts with the selection of an appropriate device. This includes weighing out the pros and cons, determining what contaminants exist in your water, and the amount of space or area you have to work with. Then, once the selection is made, the design and calculations for the system can be done. And lastly, testing your prototype on an advanced design software like SuperPro to maximize the efficiency of your system and to double check all of your previous calculations. When designing for your system, there are many critical parameters you need to be familiar with in order to produce the best operation. A few major ones include the flow rates and concentration of contaminants in wastewater being treated, the specific dimensions and packing material of your system, and appropriate constants, factors, and ratios being used during calculations. Keeping all these in mind, you should be able to design the best system available. The physical mechanism that is used for air stripping takes advantage of Henry's law. This states that at a constant temperature, the solubility of gas is directly proportional to the partial pressure exerted by the gas. An important consideration for this law is the fact that species have a preference to exist in equilibrium in nature. Conceptually, this makes sense, since the greater the force exerted on the water by a gaseous compound, the more resistant a compound will be to water's natural sequestering properties. Also, a key component is the Henry's law constant of the compound. This is represented by K in the Henry's law equation. This is a representative value for the ratio of the concentration of a compound in air versus the concentration in water. This is used as an indication for the affinity of a compound to exist in a gaseous state rather than a liquid state. Due to this, compounds with high constants and high partial pressures are favorable for air stripping. In addition, the typical cut point for air stripping to be a viable remediation method is a constant of 0.01. Since temperature and pressure are directly proportional, compounds with lower Henry's law constants could be used with air stripping if an external source of heat is applied. For the success of air stripping, a very high surface area inside the units is required. This is accomplished through the use of designing packing material. High surface areas provide a large amount of space that is able to be occupied by the water. When air is forced upwards through the unit, it will pass over the entirety of the water-occupied surface area. The increased surface area will encourage volatilization. Also, an important aspect to remember for this process is that there is no chemical breakdown of the contaminants. The process relies on the physical removal of pollutants from water to air. Due to this, the air becomes contaminated and cannot be directly released into the atmosphere. As such, additional treatment must be done on the air. This is typically accomplished through a form of granular activated carbon that takes advantage of adsorption to remove the pollutants from the airstream. The table on the right shows values for the Henry's constant and solubility of some common compounds able to be treated with air stripping. These values are based on a temperature of 25 degrees Celsius or 77 degrees Fahrenheit. Note that the range of constants are near 0.01 for some compounds like tetrachloroethane, or up to 9 and 27 for gases like ethylene and methane. Also, notice that Henry's constants are not directly proportional to solubility values due to the varying partial pressures exerted by different compounds.
Air sparging consists of several components and equipment in their system design. The first one is its well orientation, placement, and construction details. Depending on conditions of the site, the sparge wells of an air sparging system is either vertical or horizontal in orientation. This depends on the depth and the amount of wells needed. So for the deep contamination area and groundwater with less than 10 wells needed, vertical wells should be used, while for a shallow groundwater table and needing more than 10 wells or an affected area that is under an operational facility, horizontal wells should be used. In some cases, a trench may also be used as an alternative to wells. The placement, which is the spacing, and the number of wells needed will depend on the total area contaminated that is to be cleaned up, as well as the radius of influence of the design. The diagram displayed here shows the different possible well configuration designs used for an air sparging system. As you can see, there are 4 different configurations shown. There's the space configuration, nested wells, horizontal wells, and a combined horizontal and vertical wells configuration. The goals are to optimize influence on the plume, which would maximize the system's removal efficiency, and also give optimum monitoring and extracting points to make sure that the plume migration is minimal and that there is no migration that is undetected. This can be determined using a number of methods. However, specific site conditions and design components, such as areas of high contaminant concentrations, the incorporation of a surface seal for the design, and sites with stratified soils with different permeabilities in each stratum must also be taken into consideration when determining the spacing between wells and the number of wells needed. The wells are usually made out of stainless steel and sometimes PVC that is about 1 to 5 inches in length and typically 5 centimeters in diameter, and that could be larger at higher flows. However, plastic can be dangerous under high pressure and temperature. The second component is the manifold piping, which connects the sparging wells to the air compressor. Depending on the operations of the site, ambient temperature, and local building codes, the piping is either set above grade, which is the ground, or below grade, which means below ground level. However, below ground level is typically more common. The piping is either manifolded in the equipment area or gets connected to a compressor in which the wells are set in series. In addition to that, it should also be sloped towards the well so that the condensate or the groundwater entrained will flow back towards the well. The pressurized air distribution system can be made of either metal pipe or rubber reinforced air hose. The picture shows an above grade air sparge manifold setup with a control equipment like the control valves, which I will discuss more later on. The next component is the compressed air equipment, which is used to supply the air into the wells. This is typically an oil-free compressor or a standard compressor equipped with air filters. The air filters are needed so that no additional unwanted contaminants gets injected into the saturated zone. It should be operated continuously and at the maximum expected flow rate and pressure to provide flexibility during the full operation of the system. The picture here shows a compressor with a filter on top. The next component is monitoring and controls. In an air sparging system, the parameters that are typically monitored are air or vapor flow rate and pressure. The equipment used for monitoring would help determine appropriate system adjustments by the control equipment by providing the necessary information and tracking the progress of remediation. Monitoring equipment typically includes a flow meter, which can be an inline rotameter, orifice plate, or a Venturi flow tube, or even a pilot tube. A pressure gauge, which can be a manometer or a magnehelic or vacuum gauge. An air or vapor sparge temperature sensor, which can be in the form of a thermocouple or a bimetal dial type thermometer. And a sampling port, which can be a hose barb or a septa fitting. The control equipment includes flow control valves or regulators, which can be ball valves, gate valves, or other valves. Finally, the last component is an additional remedial technology system that is optional but is often used alongside air sparging, which is a soil vapor extraction or an ENVSE system. This system controls the vapor plume migration so that the potential for adverse vapor migration impacts gets reduced. It normally consists of control valves, flow meter, and sampling ports for monitoring and controlling the system, as well as an air or water separator, an air filter, a blower, and a vapor treatment equipment. This picture here shows an SVE system where you can see the main components, the blower, which is that yellow thing on the left. That big tank is the separator, and the thing above it is the air filter. Here is a simple diagram that lays out the connected components of a typical air sparging system and the SVE system that I just discussed. As you can see, air goes through the air filter all the way to the wells, and then the soil vapor extraction system extracts the vapor where it gets treated in the vapor treatment and then out.
For cost-risk analysis of air sparging, air stripping is used to separate VOCs from water. It is ineffective for inorganic contaminants. Henry Law's constant is used to determine whether air stripping will be effective. Generally, organic compounds with constants greater than 0.01 atmospheres meters cubed per mole are considered amenable to stripping. Some compounds that have been successfully separated from water using air stripping include BTX, chloroethane, TCE, DCE, and PCE. The following factors may limit the applicability and effectiveness of the process. The potential exists for inorganic or biological fouling of the equipment requiring pre-treatment or periodic column cleaning. Sometimes it's only effective for contaminated water with VOCs or semi-volatile concentrations with dimensions Henry's constant greater than 0.01. Consideration should be given to the type and amount of packing used in the tower. Process energy costs are high. Compounds with low volatility at ambient temperature may require preheating of the groundwater. Off-gases may require treatment based on mass emission rates. Some of the cost drivers for cost-risk analysis are surface area, which is in regards to the quantity of air sparge points, as well as depth of the contamination. Obviously, the farther the leak has seeped, the greater the drilling costs will require. The following slide is an overview of the price breakdown. It's an assessment gathered from the Remediation to Technology Screening Matrix and Reference Guide. The price breakdown is 2 sites, small site and large site. The key components of this chart to note are the XC2 air stripping cost is between $42,000 and $49,000 for a small site, whereas a large site can be anywhere between $165,000 and $209,000. However, that's just the stripping cost. There's obviously additional costs that go into the project. It's also important to note that the gallons treated for a small site are around 52,000, whereas a large site can be over 1 million. When you divide this by the total marked up cost, the cost per gallon for a small site ends up being 0.002 cents, whereas a large site is 0.004 cents. Clearly not even 1 cent per gallon for either treatment processes, regardless of site size. However, when you're processing that many gallons to be treated, the cost will add up.
The case study that we chose for the real-life demonstration of air stripping is the TCE remediation project in the Edwards Air Force Base, California. The Air Force Base is located within the Antelope Valley and Mojave Desert of Southern California. It is situated approximately 19 miles northeast of the city of LA. Military activities at Edwards Air Force Base began in 1933 when the Army Air Corps established a bombing and gunnery range in this area. It became formally known as Edwards Air Force Base on December 8, 1949. Since 1951, the primary mission of the base has been aerospace weapon system developmental testing and evaluation. Edwards Air Force Base was and still used as an aircraft research, development, and testing program. TCE was used as a solvent in aircraft maintenance, mainly to degrease and cleaning, and it is also the main contaminant that will be removed using air stripping for this project. The figure here is a map of the groundwater basin in Antelope Valley, marked by the blue shaded area. The groundwater flow is shown by the blue arrows, and the general contaminant plumes are shown by the red shaded area. According to the Community Involvement Plan, the contamination is a considerable distance from the populated areas, and based on groundwater flow and transport rates, it is unlikely to migrate to populated areas within the next century. In the future slides, I will be discussing the data for the Lumen Ridge on the top right side of the figure. Now I'm going to start talking about the geological data of the site. The site consists of unconsolidated sediments overlying granite bedrock. The sediments are alluvial and lacustrine deposits of sand with some gravel and smaller fractions of caliche, silt, and clay. The following are the hydrogeological data that was measured. Groundwater occurs at 25 feet below ground surface. The vertical hydraulic conductivity of the aquifer is 1.157 times 10 to the negative 5 feet per second with a vertical gradient of 0.1. The horizontal conductivity is 1.157 times 10 to the power negative 4 feet per second with a gradient of 0.005. Previous investigations identified the maximum concentration of TCE in the area to be 502 micrograms per liter, average concentration of 300 micrograms per liter, and the maximum concentration up gradient of the demonstration site were as high as 3,400 micrograms per liter. The technological application is used for remediation of TCE is an in-well stripping system which includes the monitoring network used on site. The first part is obviously the treatment well, where water is injected into the well. The treatment well was completed to a 50 feet below ground surface with a lower screen from 40 to 50 feet and the upper screen from 3 to 18 feet below ground surface. There are 5 monitoring wells that are constructed to monitor the concentration of contaminants in the groundwater around the treatment well. 3 piezometers are also used to determine the groundwater levels on site. There are also 3 flow sensors and 2 characterization wells around the treatment well. A special characteristic of this case study is that it uses a treatment trailer instead of building a permanent structure on site. This is to make it easier to move the equipment from place to place as the contaminants flow down gradient. The trailer is equipped with an air compressor, blowers, generator, instrumentation to control the system, diesel fuel tanks, and a high-efficiency particulate air filter. As shown in the figure, air is injected through the sparge well into the base of the well by the compressor. This creates a bubble column that lifts the water and strips the contaminants in the air's water separator. The contaminated air is then vacuumed off and sucked through a carbon granular activated canister. The treated air is then released back into the atmosphere while the treated water is pumped back into the well. The operation settings are as below. The operation went on for 191 days continuously with a water pumping rate of 7 to 8 gallons per minute and an air injection rates of 34 to 62 cubic feet per minute. The end results of the remediation are divided into two parts, the upper aquifer and the lower aquifer. The upper aquifer, the zone of influence defined by TCE reduction, had at least 50 feet radius, with a concentration reduction of 160 to 5 micrograms per liter, with an approximate removal efficiency of 97%. For the lower aquifer, however, the zone of influence has approximately 10 feet radius from the treatment well, and a concentration reduction of 270 to 173 micrograms per liter. The lower removal efficiency is said to be caused by a lower permeability layer at about 44 feet below ground surface, which limits the recirculation of the water into the treatment well. The average stripping ratio of the whole system is about 90%, and the total expenditure for the remediation process is about $870,000, which includes the cost for assembling, operation, and maintenance, as well as for the other additional personal equipment and trailer. The system was later moved to an area of higher concentration at site and has been operational since December 1997.
Air stripping describes the process of transferring volatile organic compounds, or VOCs, from water to air. VOCs describes a group of carbon-containing compounds that can evaporate quickly at room temperature. The compounds can easily change state from liquid to vapor. Examples of VOCs, including the toluene, trichloroethane, benzene, xylene, and trichloroethylene. Air stripping incorporates passing of water through an underground water that has impurities in an above-ground water treatment system. When the air passes through the water containing VOCs, its surface area increases and makes the VOCs evaporate faster. Moreover, air stripping has applications that make it a fantastic technology. In the industry, air stripping is used to separate VOCs from the water. Nonetheless, it is ineffective to inorganic contaminants. Experts use Henry's law constant to determine whether the air stripping will be sufficient. Henry's law is a quotient of the contaminant at a balance in the liquid and gases states. As Henry's constant increases, the evaporation rate, or volatility, rises. Compounds such as BTEX, DCE, chloroethane, PCE, and TCE are examples of components that have been stripped from contaminated water. On the flip side, air stripping has limitations and concerns that hinders its development. First, it has substances such as bacteria, fungi, and algae that can foul the system. For that matter, air stripping calls for pre-treatment or periodic column cleansing. Second, the system can transfer contaminants from air to water or soil. In the process, contaminants are not destroyed. Hence, it is important to ensure airstream is treated before it is released into the air to avoid air pollution. Third, the cost of power used in air stripping is high. In practice, air stripping requires a huge amount of energy during its operations. For example, a carbon air purification requires 0.5 kilowatts per meter cubed. In addition, air stripping is useful only on water that is contaminated with VOC or semi-volatile concentrations within the limits of 0.01 Henry's law constant. Experts advise that contents with visual impacts that are associated with air strippers should be considered because they are viewed as a disturbance when located in a residential area. Nonetheless, the limitations and concerns of air stripping can be managed through being careful with the type and amount of packing used in the tower. Moreover, it is important to mind the location and installation of the plant since air stripping should be checked carefully to avoid noise and odor problems. In some instances, it is important to treat off-gas based on mass emission rate. Moreover, components that have low evaporation rates at ambient temperatures requires to be heated while in the groundwater. In fact, doing so helps in minimizing the risks that come with air stripping, especially environmental degradation. In brief, air stripping is a vital technology in the removal of VOCs in contaminated water. Often, it is applied as a part of the groundwater pump. Nonetheless, this technology is limited because of air and noise pollution. It is also expensive to run a plant for air stripping because it consumes vast amounts of energy. Thus, care must be enforced during its operations to avoid losses and harm to the environment.
As previously noted, soils contaminated with volatile and semi-volatile compounds are the principal candidates for air stripping remediation. Gasoline is one such volatile compound, yet it contains 10 to 20% of relatively non-volatile components that will not be readily removed with air stripping. That in itself can limit the effectiveness of the remediation. This table from Gregory et al. Explains that shallow, unconfined aquifers that have high permeability and high hydraulic conductivity tend to have the highest efficiencies. These characteristics ensure water can easily enter the aquifer, evaporate with the volatiles, and exit the system without leaving a significant amount of contaminants absorbed onto the bulk rock. Deeper aquifers require higher pressures to get the water to the contaminant. That extra space means it is more likely for the volatiles to escape from the wastewater. If there is fine grain material, the volatiles will likely cling to the grains more strongly and make the technique less effective. This graph contains multiple volatile contaminants that are often removed with air stripping, specifically ethylbenzene, benzene, xylene, and toluene. These are some of the typical contaminants that were discussed earlier. The overall trend is a decrease in volatiles. There is a rebound in contamination after the first 200 days. This is when the volatile components were deabsorbed from the bulk rock. That increased contamination is removed again by day 300 of the air stripping. These results have an average efficiency of 98% of the contaminant being removed within 600 days of the start of air stripping. These are ideal conditions for air stripping remediation, so this scenario represents the uppermost range of efficiency. The average range of removal rate of contaminants is from 60 to 65%, with the maximum being well over 90.